Hey everyone, I'm Maria Hernandez, a senior in computer science at the University of Tennessee Knoxville, working with the Nordic Lab. I've been involved in various research projects in microelectronics and artificial intelligence. Additionally, I served as a TA for several lower and upper level computer science courses over 4 semesters. In today's video, I'll talk about our novel low-power dynamic circuit design with steep switching hyperfed. First, I'll give a motivation and introduction to our technique. Then, I'll talk about phase transition materials and hybrid phase transition FETs. Afterwards, I'll discuss dynamic logic circuits. Subsequently, I'll explain the topology of hyperdynamic logic gates and the methodology we used to analyze these circuits. Then, I'll discuss the initial results. Lastly, I'll describe 2 additional analyses we performed to optimize the parameters of our design and corroborate its robustness, which are sensitivity to insulating and metallic resistance and Monte Carlo variation analysis. Dynamic logic circuits are an advantageous alternative to static CMOS, since they have an increased speed and reduced implementation area. However, dynamic circuits suffer from leakage current during the evaluation period, causing significant degradation in the output voltage. Existing solutions to this leakage issue, such as using a keeper transistor, increase the overall area of the circuit. Today, I'll discuss a novel PTM-based model that significantly reduces the output degradation in low-power dynamic logic circuit, even under random process variation and without increasing the layout area. Phase transition materials, or PTM, are entities that display abrupt change in resistance due to insulator metal and metal insulator transitions triggered by external stimuli, including electrical. One of the applications of these materials are hyperfets. In hyperfets, the PTM is connected in series to the source of a standard FET, and the operation of the hybrid device is governed by the characteristics of the transistor and the PTM. The purpose of the hyperfet is to reduce the leakage current in the off state of the transistor, enhance its switching characteristics, and achieve higher on-off ratio. Dynamic logic circuits are driven by the clock signal at the header and footer transistor. Contrary to a static CMOS, the logic function in dynamic circuits is implemented only by the pull-down network, considerably reducing the layout area. In dynamic logic circuits, the pre-charge mode is when the clock signal is low and the output charges to VDD by the header PMOS transistor. During the evaluation mode, the clock signal switches to high, turning on the footer NMOS. In this case, the output is selectively discharged depending on the input combination. However, even when the pull-down network is turned off, leakage current flows through it gradually, causing voltage degradation at the output. This makes cascading difficult and may lead to logical failure. We utilize the hyperfet's properties in a simulation-based approach to reduce the leakage current in dynamic logic circuits. We performed the simulations in EdgeSpice using 14nm predictive technology model for the baseline transistor. Our hyperfet model was calibrated with parameters for single VO2 and designed to exhibit a similar on-current but approximately 3 times lower off-current than the baseline transistor. In our design, PTM is augmented with a pull-down network to provide high insulating state resistance when this network is off. When it is on, the PTM is metallic and the output discharges normally. Such augmentation comes with zero area penalty as the gate pitch and fin pitch remain the same. To verify our proposed concept, we implemented the 3 fundamental standard dynamic logic gates, NOT, NAND, and NOR, and compared them with our suggested hyperdynamic variants, named HD-NOT, HD-NAND, and HD-NOR. Due to the high insulating resistance of the PTM when the pull-down network is off, the leakage current drastically reduces in all 3 hyperdynamic gates for all possible input combinations. We also analyzed the effects of insulating and metallic resistance on the voltage degradation and offset voltage in all 3 gates, and compared these voltages with the dynamic ones. For a constant metallic resistance around 100 ohms, the voltage degradation decreases with increasing insulating resistance. For HD0, our technique yields significant benefits if the insulating resistance of the PTM is considerably greater than the roughly 1 megaohm of state resistance of the baseline transistor. We evaluated the effect of the metallic resistance on the offset voltage, keeping the insulating resistance constant at 18 megaohms. For HD0, our design works if the metallic resistance of the PTM is negligibly compared to the on-state resistance of the baseline transistor. This metallic resistance should be lower than 1 kilo ohm for the output to discharge fully. We performed similar analyses for HD NAND and HD NOR, obtaining alike results. The HD NAND is strongly sensitive to the input combination, thus the limits for the optimum resistances are correlated with it. Finally, we compared the variation tolerance of dynamic and hyperdynamic gates using a 1000-point Monte Carlo analysis. In dynamic circuits, process variation leads to a distribution in the threshold voltage of the transistor. In HyperFETs, the PTM imposes additional distributions in the insulating and metallic resistances. We used Gaussian distribution with 3 sigma variation for all applicable parameters, and probed the voltage degradation and offset voltage for both designs. Our simulations indicate that even with the extra sources of variation, on average, our 3 proposed hyperdynamic gates have less voltage degradation than the standard ones. Particularly, HD NOR performs better than D NOR even in the worst possible case of variation. In summary, our PTM-based dynamic logic circuit effectively reduces the voltage degradation in all 3 fundamental gates for all possible input combinations without any area penalty. To ensure a stable operation in our design, high insulating state resistance and low metallic state resistance is desirable. Lastly, even with extra sources of variations, our proposed design continues providing benefits over the standard one. Thank you so much for watching. See you all in the next video.